am as usual. If you need paper, raise your hand. Need a pencil, raise your hand. All right. So today's topic, how fast do things move? They're traveling in a circle. Now that could be someone who is doing donuts, right, in a parking lot with a car. It could be a pitcher who's winding up to throw the ball. It could be anything that moves in an arc. Physics can be used to help calculate the speed things are moving at in an arc, because you've learned how to calculate straight lines pretty much, right, for now. And real life actually has more arcs than straight lines. The gravity, air resistance, and something called friction. So join me at the lecture folder on Schoology and click on 01 Centripetal Acceleration. And I will record this on screen. Minimize this. We are recording. Okay, so this physics problem, start in a moment. She just left. She's in the career center. Okay. There's a 150-gram ball at the end of a string, and it's revolving uniformly in a horizontal circle of radius 0.6 meters. The ball makes 2 revolutions in a second. What is its centripetal acceleration? So how fast is it moving in a circle? And if you think about it in slow motion, the ball that's at the end of the string does go in a straight line for just a tiny second, and then it gets pulled down, and then tries to make another straight line, and then it gets pulled down. So you can kind of think of a hexagon. That's how the ball's really moving if you zoomed in like a million times. So the ball's always trying to move away in a path perpendicular to the center, but the string has a force that pulls it in. The same thing with the moon and the earth. The moon wants to pull away and release freely into the solar system, but the earth has gravity that pulls it back down just a little bit, so that the earth so that the moon travels in an arc. So it curves again, and it curves again. And if you took chemistry, you all know about the atom, and the electron tries to escape the atom, but the electron gets pulled right back in by the proton and can never escape unless there's a chemical reaction. So those are some examples of things that try to curve away, but they just can't because of the centripetal force. And in this case, we're going to solve centripetal acceleration, how fast it is being pulled in. It's easiest to think of it as a picture. Oh, let's go ahead and open this up. So the ball is at the edge of this circle, and it wants to be released in a straight line. Kind of like when you hold hands with another person and then you spin them around, and if you let go, they're gonna go flying, right? The same thing with the ball, but this string doesn't let go of the ball. The string pulls the ball right back in as it tries to escape. But this arrow just shows the direction for like a millisecond. Now, with period one, I really confused the students because there are 6 steps to this physics problem, and I didn't put them all side by side. I would put one step in the upper left and then one step in the bottom middle, and it just was really confusing, and I felt awful. So I hope this grid helps a little bit. The first step to solving a problem where the object is traveling in an arc is to use a new triangle. And this triangle is called v squared over ACR. Now, v squared is your velocity. AC is the acceleration of centripetal acceleration. So the ball trying to move towards the middle because of the string, that's the acceleration. And then the radius is kind of like the length. In your warm-up, you saw X is over VT and F is over MA, the same as V2 over ACR. This problem's asking for centripetal acceleration. How fast is the ball moving towards the middle where that person's holding the string? So AC is the variable. And if you know how to use triangles, the top portion is your numerator, and then the bottom portion is your denominator, and you've got your formula for the problem. Now we don't have V because V is velocity. There's mass, there's length, and then there's something called revolutions. So in order to find A sub C, we have to find V. V is inside of A sub C. So how do we find V? Well, it was in your warm-up, that triangle, X over VT. So we just write down what V equals. V equals X over T. This is review. Many of you did very well on the exam last week. But we don't have T. So now we have to find T. But before that, length of a circle is not radius. In fact, length of a circle is not diameter either. For physics, length of a circle is the length around the circle because that's the path of the ball. So we have to find the formula that gives us length of a circle, and then we'll put it in this X, and then we'll find V, and then we'll find A. All right. So I'm glad this is recorded because it would be very confusing to follow this when you are just joining as an absent student. So this triangle is actually the same thing as this triangle because the length around a circle called circumference is 2 pi r. So it looks like you have to memorize another triangle, but it's just the same thing. Length of a circle, length of a square, right? Length of a circle, length of a rectangle. And then VT is the same. And we still want to find V so we can find A. I had students in the back in period one trying to follow along from up here on the screen, and they sometimes copied the same thing twice, or they forgot one essential letter, and then when they were trying to do the practice problems, they were completely lost because they don't know where that letter went or why they had something written down twice. So I recommend having this open on your screens like many of you do already, so you can see up close, and then you just look up here when I'm pointing to something at the time. All right, fourth step. Fourth step is to find T, because right now T is not given. We're given revolutions in a second. So we'll find T to help us find V to help us find A. So let's go ahead and give you the formula for T. Formula for T is time equals number of seconds divided by number of revolutions. How fast does that ball move per second around the circle? So physics problem says it makes 2 revolutions in a second. 2 revolutions in 1 second. So that's the same thing as 1 divided by 2. Now we have our t. Our t is 0.5 because it was the number of seconds divided by number of revolutions. The physics problem said it right here, 2 revolutions in a second. Now let's plug it into our v equals 2 pi r over t, and then we'll plug that into a equals v squared over r. So 5th step. Plug it in. I'm going to call on a student, do the calculation for us. 2, period 1. Period 1. All right, Carolyn, grab a calculator and take 2 times pi. Now, if everyone looks at their calculator, raise your hand if you need a calculator. Buddy, grab a calculator. Carolyn, hit 2 times, and then pi is on the left side. And then you're going to hit times 0.6. And then tell me what you get. 3.77. I like how she rounded. It was 3.769. So 3.77. And then the denominator is 0.5. So keep going, Carolyn. Give me 3.77 divided by 0.5. 7.754. 754. So this is what we're going to use inside of this. Thank you, Carolyn. Let's go to our last step. Our last step is plugging in acceleration, solving for acceleration. It's 7.54, right? Not 755. Okay, don't forget the decimal, everyone. Mine got erased, or I carried it off somewhere. So plug in 7.54 squared divided by 0.6. Let's have someone who's here. Elijah, grab a calculator and plug in 7.54 squared divided by 0.6. Just do it all in one calculation. $94.75. And if you wanted to see the steps of it, then you could just rewrite it as 7.54 squared equals 56.85 divided by 0.6. But the final answer is 94.75. So that's how much force, I mean, that's how fast the ball is moving towards the middle. But then it starts to slow down because the ball wants to get away, but the string brings it right back. So the ball's going like this, and the string pulls it back down. The ball's going like this, string pulls it back down. Ball's going like this, string's pulling back down, right? But much, much faster than what I just showed you. That's how things move in an arc. They try to move in a straight line and get pulled down. But that's how fast it's moving downwards. All right, that's our first centripetal acceleration problem. We're going to do one more, and then I'm going to give you your practice problems. I'm going to stop the recording.